Good afternoon, everyone. My name is Chris Valentine. Welcome to a DevOps State of Mind, Continuous Security with Kubernetes. I've been with Red Hat for about 13 years. I work with strategic partners and customers up and down the West Coast. And today's talk centers around security and Kubernetes because they're fast becoming integrated with OpenStack. And we'll talk about how you can manage the security in such an environment. First off, Andy Grove talked about how only the paranoid survived back in the 90s. And this isn't about security, but it's about strategic inflection points. It's when a company is surrounded by disruption and change, and they need to make a decision. Do they stay the course and potentially get passed by the disruptors, or do they pivot and change course and potentially thrive? And there are many companies who are having to make this decision right now across all sorts of industries, such as retail, finance, media. Media and transportation. Software is quickly enabling these disruptors to stay ahead of the competition by quickly innovating faster than the competition. So how does the typical enterprise keep up when the typical enterprise takes 6 to 9 months to release new software to production versus the disruptors who are able to deliver software every hour or every day or every week? And the challenges, as I've talked with customers up and down the valley, have been that dev, test, and production or operations have all evolved into independent silos, including the security team. And the result is that it's very cumbersome to move software from environment to environment because there's limited resources. The developers don't have the tools or the platforms they need when they need it. There's security bottlenecks, manual processes to get approval to make changes or to have a physical standby data center to make that change. And when it comes to change, the amount of change in these monolithic applications is a large change set. A large change set means more bugs, longer testing cycles. And as a result, they have an extended feedback loop, right? A long delay between when a customer requests something or when there's a security notification to when they could actually deliver that update into a production environment. And as they siloed off, just like in nature, if you live on your own island, eventually there'll be drift, environmental drift from one island to another or from one environment to another, and they will no longer be the same. So as a result, there's this evolution in how applications are developed from a process, technology, perspective in terms of reducing organizational silos, breaking down those walls, bringing together dev, test, and operations, similar to the open source world in terms of collaboration and transparency as well. Also, the ability to accept failure in your application environment as a normal, right? It's much more expensive to develop something for 100% uptime versus 99%, and not everything needs 100%, as well as a longer lead time. Also, implementing gradual change, right? Incremental improvement, ability to deliver that change quicker through the process. And also, leveraging tooling and automation is a key part of DevOps as well. And measuring everything so that you have that feedback, you're able to pivot and change direction quickly. But what about security? As I've talked with customers when I first started Red Hat, security discussion typically started and ended with the operations team, right? Developers, testers really weren't as involved in terms of security discussion. And when it came to how do you patch and address security issues, typically I got blank stares when I talked about patching their overall environment. Instead, they were just patching their servers that were in the DMZ. And so certainly things are changing. These logos represent over 1 billion data breaches in the last few years from some marquee customers and brand names throughout North America. And what is the reason for these breaches? Our statistics show that 36% is because of employees not properly taking the necessary security measures. Another third are due to outside breaches. 14% to unpatched or unpatchable servers. These are the outlier servers, the ones on the older versions, the ones that have end-of-life support policies without patches. Right? And then internal attacks, another key area that security issues are being sourced from. Shadow IT, and then also folks bringing their own devices or unmanaged device into the enterprise. And so security must evolve and keep up as IT changes to keep up with the business. As application architecture rapidly evolves to a microservice base, as the development process moves from a waterfall to a DevOps, and the application, the underlying infrastructure moves to a private cloud built on OpenStack or a hybrid cloud incorporating public cloud as well. And so these key changes from a security perspective, what are the implications? First, the move to a hybrid cloud environment. We're more and more seeing folks have a dev test environment, perhaps on a public cloud, and their production environment on a private or virtual environment within their firewalls on their data center. And so from a security perspective, the security perimeter is rapidly expanding to not just their data center, but also having to incorporate services or environments that are not under their control. A second trend we're seeing is also in terms of distributed applications. Right? The application is no longer just a three-tier architecture sitting behind your firewall. Right? You have applications on-premise with data stored on-premise, but then some applications are accessing data remotely off-premise, or those applications are also running off-premise as well, especially as they move from a monolithic application to one that composes of many microservices. And another trend is that how the applications are developed, the movement towards DevOps. This is driving the change in culture, process, as well as technology. It has many implications because the expectation of the business is now that you can deliver software in a matter of minutes or hours to a production environment. How does security get incorporated into that? And so that's where you see this movement, not just of DevOps, but DevSecOps. That's integrating security into DevOps as part of the culture, so a security-first mindset and importance and prioritized in terms of the delivery, as well as automating the process of how security is incorporated into that CI/CD pipeline in your DevOps environment. And leveraging tools, perhaps open source tools, to automate security enforcement, detection, and policy. Take a look at an example. You know, back in the 90s when Andy Grove talked about only the paranoid survive, they were going through this Pentium bug. And Andy saw that they were not responding quickly enough to customer feedback. And so the fab had traditionally been the key differentiator in keeping Intel ahead of the game. He also saw and recognized that they need to have just a strong software factory sitting behind this fab. And so he made a couple of changes. One is they started developing their chips on x86-based hardware. They also rapidly expand their x86 Linux infrastructure to provide a large-scale continuous validation or continuous integration farm where the developers could submit a new design and get instant feedback from a security and a functional perspective, and so they could detect those issues early and eliminate them quickly. Another key part of the evolution of DevOps is about continuous build and continuous delivery. You know, software is a huge part of this automobile factory, the Tesla automobile factory, in producing reliable vehicles quickly and consistently. But also, it's enabling continuous delivery. For the first time in the automobile history, I could actually buy a vehicle, and I know that vehicle is going to get better in 6, 12, 18 months because I can receive a software update over the wire. Right? So this is business differentiating because now the company could actually provide a service, whether it's security updates or it's improvements to the vehicle, maybe better 0 to 60 time, battery efficiency, or updated applications. And when it comes to autonomous driving, it's almost a must-have if there's a security issue that they need to quickly roll out. Simply without this, it wouldn't be possible to have this type of user experience in the vehicle in a safe manner. And so DevSecOps is all about reducing risks, lowering costs, speeding up the delivery, as well as the reaction time to an issue. And it's doing this by automating security, optimizing the process, and continuously improving security on an ongoing basis, incrementally. Right? And so containers are a big part of this transition in how applications are developed, how they're architected in the overall infrastructure, because containers enable you to lightly wrap the microservice in a small image with just the necessary dependencies from a middleware and OS perspective, along with your application, and allow you to rapidly deploy and start this application and move it through your DevOps process, because you can build it once and then deploy it as is anywhere. Dev, test, production, physical, virtual, private, or public cloud. Right? And the container is a sort of a shift as well in terms of what the developer is delivering to test and delivering to production. First off, they deliver it as is without the test or production needing to rebuild or reconfigure it. And they can do that because they're actually incorporating the application runtime and the OS dependencies inside the container. But from a security perspective, who owns these layers? Right? Who's going to monitor what are the security issues for these additional layers in the container image? And what's my process for updating and addressing those issues at scale? And so one of the benefits of packaging in these components into the image file is the portability and the compatibility of the container image. I can now move that image from my laptop after it's built to a bare metal, virtual, private, or public cloud environment without having to repackage it or convert it to a different format. And so similar to the Java spec, I have a standardized runtime and a standardized image format. In the container world, you have a standardized runtime and a standardized image format, but it's for any language, not just Java. But what about containers at scale, right? Running Docker, your container runtime on your laptop is one thing, but deploying 1,000, 10,000 containers at scale in your data center across multiple data centers is another issue. There are challenges around scheduling, managing the life cycle of the container from dev into production and retirement, to monitoring the health and recovering automatically, to discovering these new services and bringing them into your load balancer automatically, to monitoring those services if there's an issue from a security or performance perspective, to responsiveness, as well as how do you scale up and scale down these services, or provide your developer with persistent storage in an automated manner, as well as orchestrating an application that consists of multiple microservices, ensuring high availability and distribution across your cluster in an efficient manner. And then security, of course. How do I address security in an automated manner, not making it more complex for my developers? And so that's where the movement around Kubernetes. Kubernetes is fastly becoming an industry standard around container management, the ability to automatically deploy your containers at scale, address storage, networking, and compute on top of your private or public cloud, bare metal, or even your virtual environment. And so Kubernetes is also a big part about enabling security in your DevOps environment, because it provides automation in your continuous delivery as well as continuous integration and being able to do that at scale. And so it fits nicely so that your developers don't have to manually write scripts to address security issues And we'll talk about in detail some of the benefits. But from a general perspective in Kubernetes, some of the capabilities it provides is the ability to orchestrate your microservice-based application. And so in this case, if I want to deploy a web server with two instances front-ending a database with one instance, I can define that. And then Kubernetes is a declarative engine. It'll actually perform and make sure that you always have two web servers in one database in this case. And so the controller manager for Kubernetes will go ahead and pull the container image from a registry and go find an available resource. For instance, on your OpenStack environment, find an available node. In this case, it put it on 2 different nodes. And then it will go ahead and deploy the database as well. So I stated I wanted 1, and so I have a 2-in-1 configuration. And then it will automatically group these together and provide a service that front ends the web servers as well as the database. And so it configures the load balancer. A software load balancer could tie into a physical as well, or load balancer as a service. And then it exposes the web server through a route to the public internet. Right? And it stores this state in what's called the data store, which is back-ended by etcd, a distributed key value pair. And another thing that Kubernetes will do is perform a health check of your microservices. So in this case, it's monitoring my web server and my database. And if it detects non-responsiveness, in this case, the web server on the right is not responding, and it does that via the monitoring and logging that's built in, it will automatically try to rectify that issue by deploying a replacement instance of that web server. So always keeping the 2-in-1 in this case. And so the controller manager took care of that, deployed another web server, adjusted the load balancer. So now you're back to 2-to-1, and it removed the non-responsive container instance. It also performs auto-scaling. So the ability to automatically scale up and scale down your services depending on certain criteria. In this case, I've set a threshold of 75% of performance, CPU utilization on my nodes. And so once that exceeded, in this case up to 80%, it automatically detected the need to go ahead and deploy additional capacity at the front end. So it moved the declared state from 2 to 3 for my web servers. It automatically discovered that new web server based on the key value pair of role equals web, and it automatically joined that to my load balancer and is serving traffic to reduce the CPU utilization down to 50% in this case. Right, so those are just some of the basics of Kubernetes. But what about security in a containerized environment? There are a lot of areas to address. First off, we'll take a look at the top row, builds, images, registry, CI/CD, as well as the container hosts. Talk about best practices for container builds. First off, the basic flow for containers is to build, ship, and run. Right? In the build phase, you're actually defining a recipe or a build file of how to build the image. Right? Where are you pulling the bits from to actually build this container image? How do you configure it? Who do you run it as well? One of the most common issues we see out in public images that are being pulled in to an environment is that they run as root. Right? You need to specify a user to run as, and most images are not specifying that. Secondly, you want to be able to ship or share that image. Right? So you build it once and then share it, and you can share it via a registry. The registry is a common access point for your dev, test, and production environment, whether it's on physical, virtual, private, or public cloud. And then you have your standardized runtime environment. Right? This is the container runtime, whether it's Docker, CRIO, et cetera. It allows you to have a common runtime across any of these environments. Some of the best practices when it comes to container builds is to treat that build file as a blueprint. If you're a developer, think of this as a make file. If you're a Linux folk, think about this as your kickstart file, right? But instead of this being unique to just how you build your OS or your application, this becomes a common syntax across all the layers, the OS, the middleware, as well as the application layer. Right? So now you have your developers, your testers, and your production operations folks all speaking the same language, using the same syntax. Don't log in to build and configure your image. This is just like in virtual machines. You don't go in and log into the VM, make changes, and then save it, because down the road you have no idea what changes were made. So when you upgrade from one major version to another, how do you extract all the configuration changes to easily upgrade? Right? Also, version control of the build file. So store that in the source code. Treat infrastructure as code, just like you do in development. Be explicit with versions. Don't specify just the latest, which is a capability. Also, each run creates a new layer. So when you are using your build file, if you specify run, it just creates another layer, and that can cause some performance degradation. In terms of collaboration and sharing, I mentioned that the build file now becomes the common syntax at all layers. This allows your application developer to define their layer, their code layer, but also inherit other layers. So your application team could build an image for your middleware. Maybe it's Node.js. And then your operations team can provide a standardized OS layer, which the Node.js team leverages. And these are all defined in the build file. Now, each team continues to own their respective layer, and they continue to own the security issues for their layer as well. And so you could do things like auto rebuild if one of the layers changes. I, as an application developer, don't need to monitor whether the OS or the application layer has changed, but automation could detect a new image is available and trigger an automated rebuild of my application. Another best practice around container image security. Right? We did a scan of the public Docker repo. 64% of them had a medium or high security issue. Not to mention, even a larger number were configured to run as root. What are the security implications? Well, running as root, that's bad because if there's an issue in the container, security vulnerability, they could get access to the host, and then they get access potentially to any container on that environment. In terms of what's in the container, when you build the container image, it pulls in all the dependencies at the middleware and the OS layer. So in this example, from left to right, we have a C, a Java, a Node.js, a Perl PHP application. And the second column, that's a Java app. And you can see the orange box rectangle is a JRE component. So that was pulled in to ensure the Java code would run. And the triangle, there's a number 66. That indicates that there's been 66 security notifications since the initial release, in this case, of the JRE that comes with RHEL 7.0. And so the story here is that not only do I need to be aware of what I'm pulling down into my environment from these public repos, but I also need a process to scan these images on an ongoing basis. Right? Another best practice around containers is to treat them as immutable. Right? This means separating out your code from your configuration and your data. Right? The code goes into the container image, so that should be very lightweight. Just your code, the necessary dependencies from an app and OS perspective. Secondly, your configuration, extract that out. You can store that in environment variables. Kubernetes provides config maps, a way to store either a file or environment variable. That configuration, maybe it's an IP address, maybe it's a tag of some sort. And then it also has a concept or an object of secrets. Similar, stored in the etcd, centralized data repository, but it encrypts it. So passwords, usernames, keys, you could store as a secret outside of the actual container image. And when you remove the configuration from your container image, right, you increase security and flexibility. And then lastly, extracting your data. Don't store your data in the container image, but leverage either a data service externally or leverage persistent storage provided by Kubernetes as well. You can front end iSCSI, NFS, container native storage, public cloud storage, OpenStack provided storage as well. In terms of container registry security, one of the first steps I see with organizations and their production or operations team is to actually set up a private registry. Why do they do this? One is it becomes a trusted source for container images in their enterprise. They know who authored it, they can version control, they can see the history. It also provides flexibility when there's an issue 18 months down the road and they need to go rebuild an older version, potentially with a security update. If they're storing all the dependencies into the private registry, they can rebuild it. They're not at the mercy of some public repository that may not keep older versions for as long as you need them. So, private registry. Also, those images going into your registry, you want to make sure you're signing them as well. In Kubernetes, you could restrict, perhaps in your production environment, launching a container image if it's not from a trusted source. And you can detect that based on the signed image. Next, continuous integration with containers. Right, so this is a typical CI/CD flow with containers. You have your developers, your operations folks checking in your build files, your source code, and then you go to a build phase. Best practice is to leverage build images. A build image is a version-controlled image that knows how to build your source code. And it can output a container image. Why is this a good practice? Well, security threats aren't all about just changing source code. They're about also hacking into your build environment. Right? So when you have a controlled and repeatable build process, you can minimize the risk and exposure to these types of security issues. And you can get closer to having reproducible builds, right? The ability to always be able to generate the same binary from a checksum perspective from build to build. Right? And then once you build these images, you store them in your image registry, you build it once, and then as your testers need it, they pull it down into their test environment, and then you deploy into production. A best practice, this is the Jenkins CI build pipeline. I can also insert a security phase into that pipeline. Right? As a part of this security process, I would actually automate the scanning of my image every time it's built. So my developer checks into source code, it then moves to building the container image, and then it moves to scanning that image, right? And running the user acceptance functional testing as well. I could either leverage an upstream scanner like OpenStack, Claire, Anchor, Black Duck. There's a variety of scanners out there. The importance is that you're running one of these scanners on a regular basis and incorporating it into the build process. And then when they pass the scan, you could tag your image, and then everyone knows that that image is validated and when it was validated as well. Also, some registries will automatically scan and trigger a security scan every time you push a new image to it as well. Continuous delivery with containers. So one of the challenges with containers is that how do you do security updates at scale? You know, currently, most production environments, if there's a security issue, they go and patch their production environment. They go right to production. Why do they do that? Well, it takes so long in a non-DevOps or waterfall type of development model to move the next version from dev test into production. And that lead time is far too long from a security perspective. With the shift to DevOps, you're able to rapidly deploy new updates into production in a matter of minutes or hours. And so as a result, you could actually go back to step one all the time. And in this case, always going back to development, generating a container image, N+1, and then pushing that new version with a security update to QA, to staging, into production. Right? And so you're deploying that whole container image through the process every time, even for security updates. And so for continuous delivery for security updates, how do I do that at scale? Right? If I have one physical server, that may translate into 10 VMs into 100 container instances. So I have a much larger problem in a microservice-based environment of deploying. So one is to reduce the size and the footprint of my containers, and two is to have an automated process to be able to continuously deliver and potentially continuously deploy updates. And so with that, Kubernetes provides deployment strategies that are built in to automatically update your environment with a newer version, potentially with a security update. And so in this talk, we'll talk about a few different strategies. One is recreate. Secondly, rolling updates. And then thirdly, blue-green deployments. First off, let's talk about recreate. So the recreate deployment strategy is an approach where you have version 1 out in production environment. There's a security notification. I need to issue an update to my environment. So I go back to development. I generate version 1.2 of that container image, and then I put it through CI testing. Once it's completed, I go ahead and tear down my production environment. And then I deploy, recreate a new environment with that new version. Right? Why would I do this? Well, maybe it's not a mission-critical service. Right? And it doesn't require backwards compatibility to this approach. So I can reduce my development time from an API perspective as well as the data perspective. And so just a lot less work, a lot easier, a lot simpler. Why add complexity? And so for some services, this might make sense. Secondly, rolling updates. This is an approach if I need zero downtime. So this is a more mission-critical microservice. Here I have version 1 across my production environment. I'm going to go ahead and test 1.2. And I'm going to gradually roll out and update my container instances to that newer version. But before that new version comes online, Kubernetes can also check and do a health check or a readiness probe, TCP, HTTP, or some other type of script to ensure that that microservices, all its requirements are fulfilled before I join it into the load balancer. Right, so I may need to validate that it can respond to another couple of microservices before I want to bring it up. And so as I gain confidence, I can deploy to a greater percentage until I get to 100%. You know, if your application is horizontally scaled, this is a good approach. If my application is built in for API and data backward compatibility, it's a good approach as well. So it knows how to talk with the older or newer data, vice versa. Also, zero downtime. and lower risk, right? Gradual rollout. As I gain confidence, I'm not going all in at once on that new version. And I could also roll back. So at any point in time, if I see an issue, I could roll back to the previous version. Thirdly, blue-green deployments. So I can automate those as well. In a blue-green deployment, I have version 1 with the known security issue. I'm routing all my traffic. I want to address that issue. So I'm going to go ahead and set up a completely different environment called green, right? Why don't we do this today? Well, today, some folks try this, but they do that by having a standby data center. Right? That's a very expensive investment. And so with the ability, through OpenStack and containers, the ability to have a virtualized environment, I can then have in number with minimal cost increase. And so with the green environment, I'm going to deploy version 1.2. It's a mirror of the blue, except for the application change with that new security update. And then I can go ahead and test that version independently. You know, we're getting to the point where I could actually route real traffic with Istio, for example, to that environment and get a preview of how it would react to that real live traffic. And once I'm confident, I can actually switch my load balancer and route all the traffic to the green. Right. So this is great if you have the self-contained microservice. Maybe it has its own data store as well. There's some additional resource overhead because you do have 2 environments stood up as one across the same physical infrastructure. You also have to do some synchronization on your data to ensure the green environment has that access. But also, it's low risk. You're never changing your production environment. You can always revert back if there's ever an issue. And also, again, no downtime. One of the other things when it comes to security updates is you want to be able to try and experiment and know what the business impact is potentially. How do you enable your developers to try this out? I mean, there's a saying that only 1/3 of ideas improve the metrics they were designed to improve, right? And so even with security, you want to make sure it doesn't have an unexpected consequence to your business. And so one of the key things around DevSecOps is also to have that continuous feedback loop from a monitoring and logging perspective. And so with A/B testing, I can use CANARY deployments. So here, version A, version B. Version B has a different recommendation engine than version A. You can see it's recommending some different options at the bottom there. And so with CANARY deployments, I can go ahead and deploy. Version 1 has a 25% conversion rate. I came up with version 1.2. Maybe it has a security fix. I want to make sure there isn't a negative business impact. Here I can see it actually improved because we packaged the security update with a change in the recommendation engine. And I'm going to go ahead and route all the traffic to that environment. If there was an issue, it negatively impacted the business, I would roll back, right, without skipping a beat. Right. So also, how about container host security? Here's some best practices around container host security. You know, containers are Linux because Linux provides things like C groups, namespace, SELINUX, seccomp, and read-only mounts to enhance your security. C groups provides quality of service, restricting processes from consuming more resources, having that noisy neighbor issue. And so dialing back CPU, memory, network, storage consumption, right, when another process needs that. Also, namespaces provide process isolation in Linux. Right? So root user ID in a container is not root user at the host. Very important. Also, SELINUX, turn that on. Don't disable, because leveraging mandatory access control allows you to restrict a container process to explicitly state what it can have access to. So even if there's security breach, it's running as root that process, it still will be restricted to what it's defined, the whitelist. Also, setcomp filters. So this allows you to limit the rights and the capabilities that it has interacting with the kernel, the container image process. That allows you to restrict. The challenge here is you have to know what your instance may need, so it's a gradual improvement. Also, read-only mounts, so mounting file systems read-only, especially /sys/proc, so that you can't edit and configure that to alter the behavior. And so some best practices: don't run as root, limit SSH access, make sure you're using namespaces. User namespaces are becoming available now on upstream. Define quotas for your resource consumption so you don't overconsume and impact your neighbors. Make sure you have logging turned on, and not only apply security errata to the container instance, but the underlying host as well. And leverage setcomp filters. So we talked about builds through container hosts. Now we have network isolation through federated clusters. Quickly go through this. First off, network isolation. So Kubernetes provides the ability through network namespaces to have multiple environments that are logically separated from a networking context. So you can have dev, test, production, all in the same infrastructure with isolated networking. It enables multi-tenancy as well. You can also define network policy. This allows you to define a policy and restrict what access a container has with another container. So you can limit and set up filters to limit the traffic between service to service. Storage security. Also, security context constraints you can define. You can also define local storage quotas. API and platform access. You can set up authentication and users and roles to limit what capabilities those users have in the environment. Very important when they have the power to provision new services. Also, monitoring and logging. So having centralized monitoring and logging, you can feed that into a system like Splunk, et cetera, or you can view it as well in Elasticsearch. Here's an example of the monitoring the services. And then lastly, federation. So the ability to set up multiple clusters and have different security contexts for those clusters. So some applications may be deployed to high security environments, or you have like dev or test in a lower security. And so with Kubernetes, you can have multiple clusters with different security contexts. And when it comes to monitoring your progress towards improved DevSecOps, here are some metrics to track compliance scoring of your container images. How frequently are you deploying these instances? What's your lead time? And what's the failure rate? As well as how long does it take you to recover when there's a known security issue to you going through the cycle of dev, test, production with that update. And then, of course, monitoring the service availability. With that, I want to thank you. I'm available on LinkedIn. My email is here. Feel free to reach out. Also on Twitter. And I'll be in the back outside if you have any questions. Thank you so much.